Hello, everyone, and welcome. Today, we're going to be talking about graphs. We're just going to start with a little bit of an introduction to graphs, some of the definitions around graphs, and then in the next video, we'll talk about actual implementations and representations of graphs in code. So to start off, let's just talk about a couple of different definitions, and let's start off with the definition of graph. Now, a graph is a mathematical object that's composed of points and lines that connect them. Mathematicians will often refer to these as vertices, potentially nodes, but there's a better chance that within computer science, non-theoretical computer science, I should say, we would hear nodes over vertices, and then both would refer to the lines as edges. Now, one of the main reasons I would say for this, vertex or vertices is just more of the mathematical terminology. Nodes makes a lot of sense for us as computer scientists, just because of sort of how we visualize this. We sort of end up visualizing it like a node in a tree or a node class that is connected to other data points through the references, through these different potential edges that exist. We also, depending on sort of the application, when we're talking about nodes, we could be talking about like within like network trafficking and stuff like that. And so nodes just often is very fitting for the practical applications or the practical implementation within computer science. That's all. Both are right. Both are totally cool. That just if you hear me use one term more than the other, that might be why. Now, symbolically, we can write a graph as follows, and this is also sort of the mathematical representation of it. G is equal to V comma E. V is going to be our set of vertices, and like capital V, and capital E is going to be our set of vertex pairs, right? That represent our edges. So just for a little bit of practice here, some examples of valid graphs. We have an empty graph that has absolutely no nodes or edges in it. So we'll have like I guess I'll do the empty set of vertices and the empty set of edges as such. Okay, we can also have a graph that has one node and no edges. Here we would define our set of vertices with just an A in it. And then here we would set our edges as the empty set as well. Again, you might sort of just see this without like the empty set symbol. Somebody might just do it like this. That would be okay too. And then here we have a graph that has 4 nodes and 6 edges. Depending on sort of your formality and how you'd want to define your different edges, we'll do vertices first, A, B, C, and D. Now there's different ways to define your pairs here, your edges. Sometimes I'll sort of informally write it like an edge AB, an edge BC, etc. But sometimes you may see edges defined actually as these like sets of vertices, A to B, B to C, A to C. Oh, I forgot the comma there. A to C, A to D, B to D, and C to D. So you just sort of, depending on the situation, might find that they are defined in different ways. And as we'll soon see, there are different ways to define that set of edges. Whoops, depending on what it is that you're actually trying to represent with that set, like the direction of the edges and things like that. But it would look something sort of generally like this. Try to get it all in one line, but I guess I can if I put it down here. The things I get caught up on sometimes are very silly. Okay, so it's very possible that I would like give you a drawing like this, and I'd ask you to reproduce it in this definition, or I could potentially give you the definition down here and ask you, given the definition of graph G, could you please draw the graph? How would it be actually visually represented? Oops, okay. So as I had said, depending on the direction of the graph, we may end up with different definitions. So let's just look at what that actually means. So we have 2 different terms here that we need to consider. We have this idea of undirected graphs and also this idea of directed graphs, also known as a digraph, because it has a direction to it. Okay, so an undirected graph will still have those edges defined as like UV or VU. So the first node that is connected to the second node. But the point being that UV and VU are interchangeable. So they're equivalent. So this edge is exactly the same as this edge. Now both edges do exist, but they're the same. They're the same line in our graph. So we just draw a single line, as we can see, A to B, and we understand that that means that like sometimes I'll like draw a little person to represent like a message or anything, but like we understand that that means that a message could walk from A to B, or the message could walk from B to C. Now, we haven't really given any practical applications yet for graphs, but maybe your brain is already starting to think about some things. We can sort of think about an undirected graph as a bunch of two-way streets between landmarks. So like even within the context of our university, we can think about like, I don't know, university center. We can think about the engineering building. We can think about the bioscience building. We can think about Duff Roblin, just sort of like all these different buildings and how you could walk from University Center to the engineering building, or you could walk from the engineering building back to University Center. There's no restrictions on which way you can walk. Both ways are acceptable. Also, just like thinking about it as like literally a map with a bunch of two-way streets. Now, on the flip side, we have this over here, we have this digraph or a directed graph where the edges UV and VU are distinct. They're not the same thing, and you can't assume that they both exist. So we would draw an edge UV actually having an arrow pointing in that direction to actually tell us, okay, what we're talking about is that you can only go one way. So if we think about like downtown and like downtown Winnipeg, don't quote me on which streets go in which direction because I have no idea. But like we have Donald Street and we'd have like I have no idea. This is gonna just be butchered really, really quickly. Carlton can only go in one direction, and Fort, and there are other streets downtown that I can't think of right now. And basically, what we could do is we understand that we could go from Donald to Carlton, or we could go from Carlton to Fort. But if we were on Fort and we want to get back to Carlton, we'd have to like go a roundabout way. You'd have to actually like make two right turns or two left turns or whatever it is to get back to Carlton. You wouldn't be able to just like turn your car around, make a U-turn, and go back because it's a one-way street. I think that that's probably pretty descriptive at this point. Okay. So we have other options here for properties of our graph or sort of definitions that come along with our graph. We have vertex and edge labeled graphs. That seemed like it turned out to be a little bit of a tongue twister. Edge labeled, vertex labeled, or node labeled graphs. We can always call this node labeled. If you have a preference for one word over the other, I will not hold it against you. So let's start by talking about actually the node labeled version, because that's what we've seen thus far, is just giving our nodes labels A, B, C, D, E, F. Super common, makes a lot of sense if we're talking about like different transit routes between cities. In Manitoba, we'd have Winnipeg, we'd have I don't like, obviously this graph isn't representative of Winnipeg, but or of Manitoba, but like we can just sort of see how there would be, these are each each of these vertices are like associated with a place, and then our edges would be like the ways between those places. And again, this isn't super representative of Winnipeg, of Manitoba, but we can just sort of get this general idea here of towns and cities and landmarks and whatever else that may be represented as vertices. So we often see node labeled graphs. It makes a lot of sense when we look at it like this, but there's also situations where we may not want a node labeled graph. For example, if we think about like a mobile network where I have a message that I wrote, like literally think abstractly, like very high level, I have a text message that I want to send to my friend, like I'm right here in the world and I want to send it to my friend right here in the world, we have to sort of do some jumping between satellites and do some jumping between potentially other people's phones to get there. So my message starts here, and maybe it can go to people all over the world. It like needs to sort of create a path to get to this other person. Maybe we use satellites to get there. Maybe we use other phone towers to get there. Whatever it might be, I shouldn't be able, as like a message, I shouldn't be able to learn any information about these different cell towers, about the satellite, about the different people, about other people's messages. So perhaps we are not labeling our nodes with anything that's public facing that you'd be able to access information from. Really, really high level, right? That's not quite how it works. But just as an example of why you may not want to have your landmarks labeled. Okay. As for edge labeling, this one is more of like what we will end up seeing more as like an optional. We often label our nodes because it makes it easier for us to like look at the graph and understand its structure. But pardon me, more frequently as like an option for us will be this edge labeled idea. And typically when we're talking about a label of an edge, we're not talking about like a name. So these aren't like street names. We're usually talking about a numerical value. And typically this is referred to as a weighted graph. Now, this could represent perhaps the distance. So each of these values is the distance between those places. Again, not actually representative of Winnipeg, but we could just pretend for a second. It could also be representative of other things like the number of stops that you would make along that path. It could be representative of how much snow you might encounter along that path, the risk factor of being eaten by a bear along that path. I'm thinking of different examples. So like maybe you're playing a video game and you have an open world, and different ways between different places in the world have a higher risk of getting eaten by a bear, right? So if I am me and I'm starting right here in Winnipeg and I want to minimize my risk of getting eaten by a bear on my way to Kleefeld, I'm going to take the path here and then I'm going to see, okay, I could go this way or I could go this way. And it looks like this way there's a lower chance of me getting eaten by a bear. So I'm going to go this way. And then I could go back. I've already come from this way. So now I'm going to go this way. And I realize, okay, my chance of getting eaten by a bear here is only 3, and now I can go this way. And my chance of getting eaten by a bear, other than this very first non-optional route, never went above 4. Whereas if I went this way, my chance of getting eaten by a bear this way perhaps is significantly higher than taking the long route around. By that same logic, if these did represent kilometers, again, going from Winnipeg to let's just say Winnipeg to Gimli, I'd go through Brandon for some reason. I'd try to go this way and I'd see, okay, if I go this way, this will take 5 kilometers. But if I go through Flin Flon, it will only take me 4 kilometers. And so what I can do is I can recognize that I can go this way through Flin Flon, and that this path from Winnipeg to Gimli through Flin Flon will take me 10 kilometers, whereas Winnipeg to Gimli through Brandon would take me 11 kilometers. And I want to take the shorter route, so I go through more cities, but it's a shorter route. So these edge labels can represent different things. And we're going to look at this more, this idea of like shortest paths and how we can sort of use this information to our advantage to solve interesting and complex problems. Now, if we have absolutely no labels whatsoever, everything is just sort of an anonymous node, everything is an anonymous edge, we would just call it an unlabeled graph, which makes sense because there are no labels. Okay, there we go. Oh, that didn't highlight very nicely. Let's just try that again. There we go. Okay. Now we have 2 different types of, now just as a reminder, like each of these terms that we're discussing thus far are like independent attributes of a graph. So something could be undirected and labeled, vertex labeled, undirected and edge labeled, undirected and unlabeled, directed and unlabeled, right? There's different combinations and permutations of what we've learned thus far in these definitions. And that holds true for this next set of definitions as well, which is simple and non-simple graphs. Now, here we go. Mostly we're going to be dealing with simple graphs. But it's good to know that there are 2 different types because in future courses, that may not be the case. Now, if there's only one edge that connects any 2 vertices, we call the graph simple. You'll notice that this has nothing to do with the directionality of it. It's just about how many edges there are connecting it. If you think about, in the engineering building here at the university, or actually let's even like think on a more global scale. Let's just think about probably like wherever you live right now and like getting to a grocery store. There's actually probably a lot of different routes that you could take to get there directly. Like maybe you can like take your bike there, maybe you can walk there, maybe you can take a car there, but all of these would get you to the grocery store. Um, and maybe like they all take different pathways, right? Like there's a walking path, a bike trail, and roads. And so what we see is that um, each of these may be representative of different pathways, of different ways to get there. We can walk to the store and walk back. We could take our bike to the store. We can take our bike back, and so on and so forth. It's also possible, though, that these could represent different like roads. So perhaps road one over here is a two-way street. Again, thinking like very much like actually roads on the street. Now, road two and road three are each um, instead one-way streets. So perhaps you take road one to the store, you can take road three home, road two to the store, road three home, road two to the store, road one home. There's lots of different ways through. This is not simple. This represents something much more complicated than that, right? And we can see that over here. But we can understand then how the idea of simplicity, like a simple graph, truly does it's talking about one way in, one way out. That's what's really important. So here we're talking about one way in, one way out. In this case, one way in, one way out, when we say simple, is in this idea of a undirected graph, right? So a reminder that we had said, where is it? Right here. It's down here, actually. So that's pretty funny. So not a reminder, a note that when we just use the term graph, we're usually talking about something being completely undirected and simple. So when we say graph here, we're talking about undirected, which means that this allows us to go in and out on the same path. If for some reason this had two edges connecting it, but each was one way, it's still like one way in, one way out. So it's just something to consider when you're trying to determine if something is simple or not. Now, on the non-simple side, we understand that this is more than one way in, more than one way out. So we can take this way in and this way out. We can take this way in and this way out. We can see that there's like a lot more to be said and done about our non-simple graph with respect to how you would go through it, how many edges you can walk to get how many different potential pathways there are, right? How many permutations of pathways. Now, within the context of this course, we're talking simple graphs. We're not going to worry about non-simple graphs, but it may help to think about it as one way in a node, one way out a node. I guess I should say a pair of nodes, really. Maybe that's a better definition. A pair of nodes. And this one is multi-way. And that's going to matter when we talk about loops and how that reflects in its simplicity in a second. So just something to note there. I'm going to just erase that so that I can keep my slides looking somewhat clean instead of running into the same issue I had in class. Okay. So another term that we want to make sure that we touch upon here is going to be this term, this idea of adjacency. Two vertices are said to be adjacent if there's an edge that connects them together. So it's not about where they are spatially, it's about whether or not an edge connects them. So it's possible that we have one node over here, node F, and one node over here, node G. And if an edge connects them, even if they're spatially far apart, like they're not like, it's not about like how closely they're located together, that's still neighbors. Okay, so edges connecting makes them neighbors, makes them adjacent to each other. So if there's a direct edge between two nodes, they are neighbors. We're going to discuss this term path soon, which is like talking about like a path you would take. And paths are defined by the number of edges. Paths equals number of edges in a sequence. And this is going to be important because we can also define this idea of two nodes being adjacent. So node A and B are adjacent if and only if the path, there, I should say, if and only if there exists a path of length 1 between those two nodes. In the next slide, when we actually define these terms a little bit better, this will make more sense. But something just to consider what I'm actually saying is that we are directly connected to our neighbors. So that means that C has two neighbors. Its neighbors are A and D. Its adjacent nodes are A and D, right? C's adjacent nodes are A and D. Now, A only has a single neighbor. It's only adjacent to C. D is a single node and it's only, D has a single adjacent neighbor. It's C, that's the only one it's connected to. B has no adjacent neighbors, has no adjacent nodes. So if we want to sort of think about this in terms of Earth, we could say that neighbors can be, you can drive to neighbors. Just as an example, you can drive to neighbors. You can go from North Dakota to like Minnesota, and you can go from North Dakota like even to Manitoba. To be honest, there's a border here, but it's still true. You can, but we can't drive to Hawaii. I don't know the Hawaii state code. You can't drive to Hawaii. It's an island, right? So, we can think about this sort of idea of adjacency and neighbors with respect to like United States or countries or whatever we want to think about. If there's no direct way to get there, we're not their neighbor. Now, we could say that, that, and to be clear, we can't get to from Manitoba to Minneapolis without Minneapolis without driving through North Dakota. So this connection, it's not that it's impossible, it's just that we're not neighbors. We have to go through our neighbor to get there. Okay, that makes sense. I think that makes sense. And yeah, and just note that we sort of make this assumption here that if we just say, oh, we're talking about a graph, sorry, where was it? Again, this one here, that when we use that unqualified term graph, we are just talking about things that we can walk in both directions of. So like a neighbor, that doesn't affect adjacency, but like if I said, oh, here's a graph, who are A's neighbors? The fact that you can walk both ways doesn't affect the adjacency here. It's still just A directly connected to C, C's directly connected to A and D, B still has nobody. Adjacency is sort of separate from the directedness of it. It's who we are connected to. All right. With that in mind, we're going to talk about this idea of the degrees of a node or the degrees of a vertex. And this is how many edges are actually connected directly to a given node. In a directed graph, so if our graph is actually directed, we have those one-way streets on them. We have to consider two different attributes, the in degree and the out degree. So if we look here at our undirected graph, and we're standing on C and we ask ourselves, what's the degree here? The degree of our node C is going to be 2, because we can go this way or we can go this way. Actually, technically, we may consider it to be 4 because we have 2 that are coming in and 2 that are going out. So in this undirected graph, we have this idea that every single, I better write this down. In an undirected graph, each edge represents 1 in degree and 1 out degree. Just because you can walk in or out from this single edge, and that fact is important. We could use that fact later. So here, B has a degree of 0, D has a degree of 2, A has a degree of 2, and C would have a degree of 4. For this undirected graph, so just considering that point that I just made, and the fact that this is true, that an undirected graph, every edge represents an in and an out, is really important. We use that to like do a lot of really funky math things. Now, if we look over on this side over here, B still has a degree of 0. D has a degree of 2, but that's because we have a degree, an in degree of 2 and an out degree of 0. So we can like actually break it down there. In this undirected version, everything is even. So if we have a degree of 2, that's because our degree in is going to be equal to D divided by 2, and our degree out is going to be D divided by 2. And over here, our C degrees was 4, and that's because our degree in is going to be D divided by 2, and our degree out is going to be D divided by 2. So we didn't break it down like that because it's just always true that it's like half of them are in and half of them are out. So it's not that they don't exist as in and out degrees here. It's just that they're always equal, right? The degree in is always equal to the degree out. Whereas over here, that may not be the case. We can see that while we have a degree of 2, we can't break it down quite so easily. We have 2 in degrees, we have 2 out degrees. We can do that here as well. We have a degree of 2 here, where our degree in is actually 0 and our degree out is going to be 2. And then here for C, we have a degree of 2. Before we had 4, now we have 2. We have a degree in of 1 and a degree out of 1. So we can sort of see how that differs. This is important for, again, if we think about like message passing, perhaps we can understand that if we want to get like really abstract with it, if you think about like passing notes in class, like your teacher, like A, B, and C are going to be students, and D is your teacher. Okay, and nobody likes B. B is kind of like an outcast and is sad because nobody passes B notes. They're an outcast. Now A is really, really popular. So A passes a lot of notes to people. And if a note makes it to the teacher, you're in trouble, right? So if a note accidentally gets passed to the teacher doesn't keep passing notes. The teacher doesn't propagate notes. The teacher like yells at you and is like, don't pass notes. And so you can see why there's no out degrees from D because there's no note passing that the teacher would ever do. But if the note reaches the teacher, that's it. It's a full stop. The teacher doesn't pass it anywhere else. It ends right here. The teacher takes your note and reads it out, and that's the end of that. Whereas, A can pass a note to the other student. The student A may get caught by the teacher. C can only get caught. C is not stealthy enough to pass notes well. So we can sort of see what might happen if we think about like passing notes like in the classroom. So like the only person here who's good at passing notes is A, because there's a chance it may get to its intended person. But everybody else is garbage at passing notes. The other chances go there, or it's a teacher, or they're just a loser and nobody passes them any notes. Okay, that was very elaborate of an example just to get my point across, but I do think it probably helped. That's okay. So here we have a path or a chain being a sequence of vertices such that there's an edge between adjacent vertices. So a path is going to be a sequence of edges effectively that connect to nodes. So I'd use the term path earlier, but I didn't actually define, like I said, oh, don't worry, we're going to define it, whatever. And I talked about how adjacent nodes basically had a path of length 1. So if we had a graph that looked something like this, this had a path of length 1. This had a path of length 1. If it was a path of length 1, those two nodes were neighbors. They were adjacent to each other. Now, it's possible to have a sequence of nodes, though. So here we could say we're going from A to B, and then from B to C, and this would be a path. This may also be denoted like this, where we would understand that A to B references this, B to C references this. So writing it like this tells us that we understand we're going from A to B, and then we're going from B to C. Now, paths don't have to start and end in the same place. Paths are just a pathway, right? It's just like a set of directions that Google Maps gives you, that that you follow in your Apple Maps or whatever it's called. So there's no the path is sort of this very generic term, and the length just being the number of edges that are in it. In the worst case of like a balanced tree or I guess even not a balanced tree, in the worst case of a tree, something like this, let's say, we can see that the worst case height of this tree would be our longest path from root to leaf. So when we've been defining h of like our height of a tree, and we've been saying, well, worst case, if it's balanced, we're going to end up with log n, where n is the number of nodes. And in an unbalanced tree, worst case, we ended up with that giant stick, right? It was technically, worst case was n minus 1, which is just going to be O of n. And we had originally said when we talked about trees that some people define height to be the number of nodes and some define it as the number of edges. And I said sort of focus on the number of edges. Here we can see why that's the case, right? So here in an unbalanced tree, we end up with just like a stick, which would give us a height of n minus 1, which is just in big O of n. So we can sort of see how that would relate back to, what we've been talking about earlier on. We just hadn't really given it a name. Okay, and now within paths, there are different types of paths. We could have a cycle. So here we define the term cycle, and it's a path where the first and the last vertices are the same, and we don't repeat any edges in that path. A simple cycle means that we don't repeat any vertices, and a graph that has no cycles is acyclic. So let's just take this over here and just discuss it with respect to these terms. We've got some highlighting going on down here. We'll just get rid of that. Is there more? Okay, sorry. So let's just discuss that. If we look at our graph here, do we have any cycles? No, we don't have any cycles. A reminder that in an undirected graph, A to B and B to A would be considered the same. So there's no cycles here. Now let's instead add another node right here. And let's ask ourselves, oops, are there any cycles now in pink? And the answer is yes. A to C to D is a cycle. A to D to C, there we go. You have to end in the same place as you begin. So ACDA is going to be a cycle. ADCA is going to be a cycle. CDAC is going to be a cycle. CADC is going to be a cycle. And we can also do that starting at D. So starting at different points, we have different cycle, different paths, cycle paths that we can define here. So we actually have 3 different cycles here that we can define. So a simple cycle has no vertex repeated, right? And since we're often dealing with simple graphs, that's just the case. Now, if this was a non-simple graph for some reason, perhaps we did something like this and something like this. We could say A, C, D, A alone wouldn't be definitive enough to tell us if it was a simple cycle or not, because we could go, that's not true. Hold on. Let me do that better. Let's say these would be probably weighted of some kind. Let's just label these edge 1, edge 2, edge 3, edge 4, and edge 5. If we went A to C to D to A to C, the path that we would need to take is edge 1, edge 2, edge 5. Why did I say edge 1, edge 2? Oh my gosh, Lauren. Edge 1, edge 5, edge 3, edge 2. And we could be a cycle, but not a simple cycle. There's no way for this to be a simple cycle. We could also take edge 2 to edge 5 to edge 3 to edge 1, edge 2 to edge 5 to edge 4 to edge 1, edge 1 to edge 5 to edge 4 to edge 2. So each of these cycles here, if you pause the video, walk through each of them, you'll see that each of those are indeed cycles that we can take through there. However, none of them are going to be simple cycles. And this couldn't possibly be a simple, and we'd have to end. I didn't even do that right. We'd have to end in the same place that we started. So perhaps I want to come up with a really good non-simple cycle. Would have to be, I guess, the most obvious non-simple. This one isn't a good example of a non-simple cycle. Let's add one more edge here. There we go. Now I can get a non-simple cycle. Oh my gosh, I'm so sorry about that, you guys. Good opportunity for you to pause and try to find non-simple cycles yourself. If we went A to C to D to C to A, this would be a non-simple cycle. So it's still a cycle, but it's not simple because we'd be walking like A to C, C to D, D to C, C to A. We had to visit C twice to make this cycle work. Alternatively, though, if all we wanted to do was find a way between visit A, C, and D, we could do it in a simple way by doing A to C, C to D, and D to A. And then depending on the weights or whatever, perhaps there's an optimal path through this not so simple graph. Okay. Again, we're mostly dealing with simple graphs, so hence the difficulty in finding an example that might help us here. But yes, and then here, are there any cycles? Originally, we had said no, which would make it what is called acyclic, since there's no cycles that we can do in this graph here. Okay. Let's move on to just a couple more examples here. If I haven't sufficiently confused you yet, let's look at A, B, C, E, F. We can see that this is going to be a path of length 4, A to B, B to C, C to E, and E to F. Fantastic. That will be length 4. It is a path, not a cycle, but it is a path. Now here, if we want to look at this one, we can find a cycle where we go from B to C. Better do it on different above it so that we can see it. B to C, C to E, and E to B. So we start and end in the same place. No edge is traversed more than once. This is not just a cycle. This is a simple cycle because we don't visit any vertex more than once. Simple cycle. Okay. Cool. Let's continue. Let's look at this next one here where we have BCB, and we can see that BCB is not considered a cycle because we'd have to go from B to C and then from C to B. And we only have one edge that we can walk along. Now, even though it's bidirectional, even though there's no direction to this edge, it's not going to give us a cycle because in the definition of the term cycle, we cannot have a repeated edge. That's the problem, right? And in undirected graphs, those two edges would be the same. So those aren't distinct. We would have to have a non-simple graph where we had multiple ways between those two nodes to allow us to have a cycle here, as we showed above. Things got complicated in that example. But yeah, if we wanted to have a cycle between two nodes, we'd have to have this. We'd have to have a non-simple graph. We even gave that like a term, didn't we? And I have already lost that term in my brain. Oh, it was just non-simple. Okay, I got confused. That's fine. Cool. All right. Those are our paths and our cycles. Okay, let's define one more term here, or I guess a couple of terms, but really these are just for your own, background knowledge. We're not going to be dealing with loops. An edge that connects to itself like this is going to be considered a loop here. Now, on that note, what does that actually mean? Here it's undirected. So the degree here is going to, depending on how you think about it, it's 4 really, because we have two different ways out. and we have two different ways in. And our edge, we have our set of edges is effectively more complicated, A to A. So we have one edge that can go in either direction, right? So we can walk this way through the edge, or we can walk this way through the edge. Okay. So loops aren't permitted in simple graphs. So like I said, we're not going to be dealing with loops right now, but they do exist, and you will see it in other courses, potentially in other scenarios where it may occur. Often we see loops in things like state machines when we're dealing with Turing machines, finite automata, stuff like that. Um, Potentially in other places as well, but that's a pretty prominent place for seeing loops on graphs. A graph that allows you to have those multiple edges between vertices, but no loops, is going to be called a multigraph. So just very quickly, when we had this drawing here, and I said, imagine we had something that looks like this. This is our non-simple graph, because there's more than one way through the, there's more than one edge connecting a pair of nodes. So this is non-simple. There's no loops. So this is also a multigraph. And this also has non-simple cycles in it. So we can put a lot of different attributes on this graph that are, some may be paired together, but I would strongly recommend that you don't try to find ways to connect them together. So instead of saying like, oh, it's definitely a multigraph if it's non-simple, like trying to make those rules probably won't help you very much. It's a lot easier to just know about the different attributes that could be assigned to a graph and just going through them. On that same note, if we added another thing here, if we added a loop here on one of these nodes, a loop here on one of these nodes, whatever, it's no longer a multigraph. Now it is a pseudograph. Everything else still stays the same. It's still non-simple. There's still non-simple cycles here, but now we would consider it a pseudograph instead of a multigraph, because we're allowing groups. We're allowing loops. This is like the biggest tongue twister I've ever had in my life. Okay. Let's just discuss connectedness for a second. So we've already seen in some of our images, like right over here, this sort of lone node. And we haven't really talked about the fact that it's lone, other than we've said it doesn't have any edges. We haven't like defined very much about that. So let's just go ahead and do that down here. So a graph will be considered to be connected if there exists a path between every pair of vertices. So what that means is a path in general. The path can be the path between those two vertices. The length of that path is greater than or equal to 1. So what does that actually mean? That means that, can we get from A to B? Yes, we can. Can we get from A to C? Yes, we can, in a path of length 2. Can we get from A to D? 1, 2, 3. Yes, we can. Can we get from A to E? 1, 2, 3. Oh, that's too far. Yes, we can. Can we get from A to F? Here, 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 here. We could have also gone like there, 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 to there, to there. Yes, we can. That's the shorter path, right? If we went A to B to C to E to F, that's a little bit longer than A to B to E to F, and there's no reason to do that. So I just redrew it. So now we can see that everything is connected to A. We now have to do this for B. We've already checked BA, so we'd have to check BC, BD, BE, BF. We'd have to then check CD, CE, CF. We'd have to check EF. So as long as all of those paths exist, we have a connected graph. If you can't tell yet, this is a permutation and combination problem. It's incredibly naturally recursive for us to sort of traverse our whole graph and make sure everything is connected one way or another, depending on the implementation of your code, though, there's actually really simple ways to check for connectedness. And we'll get there in the next lecture. We'll talk about different ways to check for those sorts of things in the next video. Okay, now on the other side of this, we are potentially disconnected. So a graph can be disconnected, and a disconnected graph is just we just not this statement, right? There does not exist a path between every pair of vertices. Now that doesn't mean that we have to have like a single lone node. It just means that every pair of vertices can't be connected. So we can get from A to B here, but we can't get from A to C. So as soon as we find a pair of vertices that are not that we can't make a path for, we know we're disconnected. So we can already stop looking. We know that we're disconnected. Now, we do have connected components here. So this, I'm going to do in pink since I just did that in pink. This is a connected component, also sometimes referred to as like a subgraph. This is a connected component. This would also be a subgraph. And then all together, this would be our graph G. So what we could do if I gave you a graph like this on the exam and I asked you to define the two subgraphs as well as the graph itself, you could let G prime equal the set of A and B, and then the set of vertices AB, right? There we go. We can let G double prime be the set of vertices C, D, E, and F, and then the set of edges C to E, E to D, and E to F. Lost a comma there. Okay. And then we could also define G itself as containing all of that information. Copy, make it way smaller so it all fits. Copy all this so it all fits. And I'll just sort of like spread this out a little bit appropriately to get all the data in here. That comma is too big. So there's my set of vertices. That's my set of nodes, right? A, B, C, D, E, F. Way too big. Okay. And then we can put our comma and we can do our set of edges beside it. So here's our set of edges. That's the first edge. This is going to be the rest of the edges. And there we go. So then that's what G is. So G is created by those two subcomponents. And given this, you could easily create this. Given this, you could create it. Given this, you can make both of these. We can start to see how questions may form for like a test to ensure that we understand the difference between a connected graph, a disconnected graph, and the components of a given graph. So like, yes, this is a graph on its own, but given the context of the wider image, we would just call it a subgraph of G. Okay. So for directed graphs, there are two different types of connectedness. So you'll know that you'll notice that if we go back up to like right here, we have, this was technically disconnected, I suppose. Let's do this. This is a connected graph. The question is it weakly connected or is it strongly connected? Now, remember that in a directed graph, A to B and B to A are not the same thing, right? So as long as each pair of these, there's a pathway to them. So between A and B, there's a path. Between D and A, there's a path. Between A and C, there's a path. Between B and C or C and B, right? So you have to sort of remind yourself that because of the directedness of it, even though in this case here, this entire graph looks connected visually, the level of connectiveness, if it's strongly or weakly connected, needs to also be defined. So if we come back down, we can actually look at those definitions right here. So a directed graph will be strongly connected if we can get a directed path between each pair of vertices. We look here, can we get from A to C in the directed way? We can. Can we get from A to D in the directed way? We can. Can we get from C to D in the directed way? We can. Can we get from D to A in the directed way? No, we cannot. There's no way out of D. So even though they are indeed connected by edges, they are weakly connected. Weakly connected here means that if it was undirected, we would be good. Okay, so we can see here that A to C is fine, but C to A is not fine because we cannot go in that direction there. So this is not strongly connected. To ask ourselves if it's weakly connected, we have to basically pretend like these are all bidirectional. So I'm trying to like ignore the fact that there's like an arrow on each of those for just a sec. Like this. I'm just like going to try to get rid of those just for a minute. And now we can ask ourselves, can we get from C to A? Yep, we can. Can we get from C to D? Yep. Can we get from D to C? Yep. Can we get from D to A? Yeah. Can we get from A to D? Yep, we can. We can see that now if we pretend like it's not directed, we can get everywhere. That makes this graph weakly connected. If we wanted to make this graph instead a strongly connected graph, a strongly directed graph, all we'd really have to do is pretend for just a moment that this went this way instead. And now, can we get from A to C? Yes, we can, right? Right here. Can we get from C to A? Yes, we can. We just have to go through D. Can we get from A to D and D to A? A to D, no problem. D to A, no problem. So it's not that directed graphs can't be strongly connected. It just depends on the situation, right? We can see now how the situation matters. C to D is fine. If we go from D through A, we can get back to C. Those are fine. So now with this arrow flipped, when we flip this, I better write this just for those of you who are trying to take notes. Flip this arrow and we have an example of a strongly connected, directed graph. There we go. Okay. Whoops. So on that note of connectedness, a graph would be considered fully connected or complete if there is an edge that exists between every pair of vertices. So another way to think about that, and again, this is separate from its strongness, weakness, right? Directedness. So a graph is fully connected if every pair of vertices, if every pair of vertices has a path of length 1. We can also think about this if every node, every vertex is a neighbor of every other vertex, right? So neighbor, 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 good. A is connected. Neighbor, neighbor, neighbor. B is connected. Neighbor, neighbor, neighbor. C is connected. Neighbor, neighbor, neighbor. D is connected. So this is a fully connected graph. This has nothing to do with the directionality of it. If all of these were directed, this could still be a fully connected graph. It's just weak. It's just weakly connected, fully weakly connected. It's a lot of different attributes that we can assign in different ways. And then here, of course, we can see that we're a neighbor of A is a neighbor of B and C, but it's not a direct neighbor of D, so it's not possible for this to be fully connected. It's not that it's not connected, it's just not fully connected, right? So this is connected. This is strongly connected. This is connected. This is strongly connected. In fact, it's fully connected. Yay. Right? So really keeping these terms separate and using them to define all the different things, you may find it helps you really understand like how to attribute the different properties appropriately. Now, to finish off this definition topic, we know the term tree, but let's just refer it very quickly back to this idea of graphs. I've said it already a little bit higher, but let's just finish it off. A tree is basically any connected acyclic graph. So this entire graph is not going to be a tree because we have a cycle. This is not a tree because we're missing a connection. I will say that it doesn't mean that there aren't subgraphs that are trees, but the whole graph is not a tree. Not a tree graph. However, subgraphs of G may be trees. So if this is G, and I say let G prime equal the set of vertices A, B, C, sorry, I'm missing my commas, but we'll just bear with me, A, B, C, D, F, and then my set of edges are A, B, B, C, B, E, D, E, and E, F. And then I say, is G prime a tree? Well, let's draw out what G prime looks like. We have an edge connecting A and B, an edge connecting B and C, an edge connecting B and E, an edge connecting D and E, an edge connecting E and F. This is a subgraph of G, right? Because it's part of it. It's just not all of it. And what we can see is that this is acyclic. So this actually would be a tree. Okay. Just get rid of that. We're going to see it lower down. Here we can see it is exactly there, a tree. This also is a tree. This is not a tree, but the subgraph that looks like this would be a tree. So a subgraph doesn't have to just be disconnected components. So here, we had two disconnected components, but we actually have lots of subgraphs because this node alone is a subgraph. This node alone is a subgraph. This is a subgraph. This alone is a subgraph. This alone is a subgraph. This alone is a subgraph. And this alone is a subgraph. Then we can cluster those into subgraphs of length 1. Subgraph, subgraph, subgraph. Then let's talk about subgraphs of length 2. That's a length 2 subgraph. That's a length 2 subgraph. That's a length 2 subgraph. Then subgraphs of length 3, just that one. Or rather, graphs with edges 3. I shouldn't have said length. I should have said edge cardinality. So subgraphs of a graph, we can be, so if we have a graph G, can do this more mathematically, which maybe will actually clear up what I'm trying to say. And let's let n equal the number of edges in G, right? So we let G be equal to this set of vertices, this set of edges, the one that we're seeing right all over here, this whole thing here. We're going to let n equal the number of edges. Then we can define subgraphs where we can figure out the number of subgraphs with n equals 0 edges, n equals 1 edge, n equals 2 edge, etc., all the way up to n equals however many edges were in our original graph. Yeah, that feels like that makes sense. Okay, let's move this out of the way as well. Ah, that's my face. Okay. Cool. So here we go. Just to follow that up, if we have a graph G with a set of nodes V and a set of edges E, then we can define a subgraph G prime with some V prime set of nodes and some V prime set of edges, where V prime is a subset of V and E prime is a subset of E. So a reminder that this is a little bit of set theory. We're talking about the set of nodes. We're talking about the set of vertices. And if you don't know, this symbol right here does mean subset, which makes sense since we're talking about subgraphs. So just to sort of drive home the point that I had before, we can make lots of different subgraphs. They can be connected, they can be disconnected. Now, the number of subgraphs can be determined algorithmically. But this is a hard problem to solve in computer science. And not because we can't do it, but because the problem grows exponentially, not polynomially, exponentially. This problem that we're talking about right now is like permutations and combinations. So this is on the order of n factorial. If I only had a graph with an A and a B in it, and I asked for all the subgraphs you could make, you could have the subgraph. So you'd have this graph, you'd have this graph, you'd have this graph, and you'd have this graph. So you can see how many graphs we have right here. With just 2 nodes, I can make 4 different graphs. I can make a subgraph of the whole, like the whole thing is the original graph. We can have a subgraph of just A, a subgraph of just B, or a subgraph of the two without their connecting edge. There's no reason why not. Those are all different subgraphs that we could create of those 4 nodes, or sorry, of those 2 nodes. Let's add another node in over here. And let's make it fully connected, because it would make a difference if it was or was not. Actually, let's start with not fully connected to make our life easier. So we still have our original graph. We have A alone, we have B alone, we have C alone. We have A and B connected with C alone. We have B and C connected with A alone. We have A, B, and C all together, but none of them connected. Am I missing any? I don't think so. So we added another node. Oh yeah, I am. I'm missing tons. Those are all the ones that include C. Then we also have the ones that don't include C. So we had A and B with C alone. We have A and B with no C. We have B and C with no A. We have A and B disconnected, but with no C. We have A and C disconnected. We have B and C disconnected. So we went from 4 graphs to, pardon me, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 to 12 graphs. 3 nodes, 12 graphs. When we had 2 nodes, we had 4 subgraphs. When we have 3 nodes, and they're not even fully connected, not fully connected, we have 12 subgraphs. If this was fully connected, we'd still be missing more graphs, more subgraphs that we could do. And we can see how very quickly this problem explodes. Now, keeping that in mind, the fact that a fully connected graph explodes like that, imagine a map. Let's just quickly do that. Imagine a map. Okay. And in our map, we've got lots of different places that need us. We are Amazon. I should come up with like a silly name for it. In quick digression, in software engineering, I'll like make up a pretend company called Notflix instead of Netflix. Comes whatever, Rob's been doing it forever, so now we use it. I need to do that for this, but whatever. We are Amazon, and Amazon needs to deliver X packages to Y houses, right? And most streets in an area don't even Y houses. It's like Y neighborhoods. There's probably lots of houses within each neighborhood. Each of these nodes is a neighborhood. Make sure it's fully connected, because usually that's, oh, we already had one going there. Usually that's the case. Is that connected everywhere? Okay, everybody, this is not connected to C. There we go. I think everybody's connected now. And now each of these different pathways have stop signs, have traffic, have lights, have distance, and many other variables to contend with. So each of these pathways, depending on the time of day, are going to take a different amount of time to traverse, right? If it's early in the morning, it doesn't really matter if we take main roads. But if it's rush hour, taking a main road doesn't go over quite as well. Let's say the Amazon truck starts their day right here at the warehouse. Okay. Actually, let's just put the warehouse. Should we make this even more complicated? Probably. We'll make it medium complicated. Here's the warehouse, and this is the closest stop to the warehouse. That's always stop one. We always go from warehouse to neighborhood A because it's really close by. We can't assume even that neighborhood A always has packages. Oh, this gets so complicated. Okay, so now the question is, what cycle should the truck take to minimize driving time? What about if we want to minimize the number of stops instead? Like stops at lights. What if instead we want to minimize distance? Because that may not equate to driving time. What if we want to minimize gas mileage, like gas, which has to take into effect driving time and distance and the number of stops depending on the vehicle? Oh my goodness, we can see so quickly how complicated of a problem it is to determine what the best path is to take. What subgraph should we be traveling along? I missed a highlighting portion here. Right, which way should we be going to ensure that we take the minimum path? Now, if I look at it as a human and I can see the numbers here for driving time, let's start with like num stops. 6 stops along that path, 12 along that path, 3 there, 4 there, 2 there, 1 there. No stops between those two neighborhoods, 4 stops between those, 3 there, and 7 there. I could look at this and probably pretty slowly but surely find an optimal path that would allow me to get from my warehouse to every single neighborhood and then back to my warehouse. Probably. Not guaranteed, but probably. If I want it to be a true, now, of course, in real life, it's totally fine for me to walk along this path twice. So looking at this, I could be like, well, I could go here. Well, actually, I would probably want to go down 2, and then I'd go 3, and then I'd go 0, and then I'd go 1, and now I'd go back up to 3. Is that the best? That seems like it could be the best. But I can look at my graph and sort of figure that out. Maybe instead I'm starting here and somebody paid for priority shipping. So now I have to go here first. Now what happens? If I have to go to here first because they paid for priority shipping, now what makes the most sense? Knowing I had to now go there, perhaps it makes more sense to go here, 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 and then here. And I visited a lot of times in that path, but maybe if all I'm caring about is minimizing stops, that's not a huge deal. I can find a path where that's fine. Because a reminder is a path is just a sequence of edges. So there's no requirement on a path. If I wanted to force it to be a cycle, that would be different. But we can see how answering some of these questions becomes not only difficult for a human, but immensely difficult to solve algorithmically and deterministically. So we can see how, if we remember our hierarchy, like this hierarchy, 2 to the n factorial, how our program grows exponentially on this side of the graph, on this side of the inequality over here. It will grow exponentially as I add more regions that Amazon driver needs to go and deliver to. I think it's pretty interesting when we start to realize just how complicated some of these problems are to solve. Okay. So on that note, graphs are used to represent a lot of different relationships and entities. So an arcade game, we can think very, very simple, thinking like a matrix, 2D array, fixed positions, players and their opponents have to move between them, right? Where we can basically imagine that as the player is moving between different spots in like a game, each of these are the vertices. Each of these spots here are like places a player can move. And then just walking to that place would be the edge. I can't directly walk over here. I would have to take a path through lots of other nodes to get over there. We can see that. We can consider navigation systems, as I just did. And we can also consider things like text understanding systems. On assignment 4, you did frequency trees. It was actually, without using the term, it was actually like a basis for a concordance tree. It wasn't a concordance tree in of itself, but it was sort of the basis of what people might use to do things with like language processing. It's called a concordance tree. And words are like each vertex, each node was representing a word. And then the edges in our case was representing a sorting order, not the syntactical relationships between them. That's why I'm saying it wasn't really a concordance tree. But we can see how we could even use text understanding systems and trees and graphs to create relationships and build out really interesting, deeper understandings. Now, things can get really complicated. We're not going to get that complicated in our implementation. We are going to consider cases that look mostly like this, maybe a little bit of complications in algorithms, but videos to come on all of those as well. With this, thanks for joining me, and I'll see you in our implementation video next. Have a great rest of your day.